university, so he's come all the way from his start to extent. So it's very nice to having him here to give us a seminar talk. So I offer it to you.
Thank you, Albert. Great. Good afternoon, everybody. So I'm based in civil engineering in the University of Leeds. I do a bit of work on infrastructure and kind of environmental context of that infrastructure. So today's talk's kind of looking at that aspect, I guess. I've called it Bridging the Gap. It's a kind of pun on the bridge context, I guess. And I'm going to talk about a particular project which is part research, part consultancy, and I'll kind of explain the context as I go along. And what I'm looking at, or what we were looking at as part of this project, was the resilience of bridges to hurricanes. But the focus is on water risks, not wind loading or anything like that. So these are small bridges where wind loading is not a big deal. So just for context, for those hardcore civil engineers that like wind loading on bridges, I'm looking at kind of water resources. So just a little bit of background about, for me, just so you kind of understand where I'm coming from in my research interests. So I worked for 17 years before I did my PhD. I worked in consultancy, overseas development, those sorts of contexts. And I guess, kind of to sum it up, I spent a lot of my time trying to make robust choices as an engineer in a world that kept changing. There wasn't always the data I needed, there wasn't always the kind of guidance perhaps, or best practice even. And essentially that curiosity as to what to do next, or what should I be doing, led me into scientific research. So a lot of the questions I had, I realised that there were postdocs doing these sorts of roles, and then I was looking at job adverts, and I realised I didn't know what a postdoc was at the time, but what I found was that they all needed a PhD, and I was like, well, maybe I should do a PhD then. And I'm still here now, so obviously enjoy it, and so that's the context. Right, so river bridges. So why are we talking about resilience of river bridges? We know how to design bridges, surely. As civil engineers, this is something we've been doing for a long time. So why is this still an issue? You know, we teach it to our students. You think we understand bridges. But when we look at the kind of research into bridges, what we find is that what's called hydraulic action, which is essentially the water interaction with the bridge, so it can be loading of the hydrostatic forces on the bridge, or it could be scour, anything to do with the water context of a river bridge, is the number one cause of bridge failure still. So that in itself kind of makes us wonder whether we really know the full picture yet. And the other interesting thing is that even where we have a process to assess the risks to a structure like a river bridge, for example, we work with Network Rail, and they have a whole process to assess risks and rank them into, you know, low, medium, or high. What we find is that even the bridges that fail, quite a few of them are assessed as low risk. So you start to think, well, you know, if our risk assessment procedures are not allocating bridges correctly, are we missing something? And there's a lot of bridges. We're talking about thousands, tens of thousands of bridges across the UK that different asset managers kind of look after. So that's the kind of context, I guess, of this talk. It's like, what are we missing? Is there some amazing research that we should be doing? And that's kind of where this came from as a project, I guess. So the location of the study is Dominica, which is in the Caribbean. It's known as the Nature Island, and you can see it's very pretty. And somewhere located here in the Caribbean, if you know the Caribbean well, you probably know exactly where it is. But it's quite a small island. It's only 750 square kilometres. It's very steep, so it has volcanoes, three main volcanoes, I think. in the centre, so a very steep system. And it has 365 rivers, one for every day of the year, as they like to boast. And so there's lots and lots of bridges. So you can probably see where the context of this is going a little bit. And unfortunately, hurricanes are very common in the Caribbean. And what we're interested in this talk is kind of how do these bridges perform under those hurricane conditions. So here's the kind of path of Hurricane Maria, which kind of went across the Caribbean. Interestingly for later, notice that the tail end of the Caribbean heads towards the UK. So that will come up later in the context. Although we're studying Dominica down here, we're also interested in the fact that tail end of hurricanes end up hitting the UK. So in the context of this project, it was about 2019 we started the project, we finished about 2022, so it was kind of a long-term project. Just when the project came in, the island of Dominica had experienced a tropical storm, not a hurricane, tropical storm, there's a subtle difference. But essentially it's kind of a very extreme weather event, lots of rainfall, slightly less wind in the case of tropical storm, but similar intensities of rainfall, 850 millimetres in about 3 days. Lots of landslides, damming rivers, collapsing, and so catastrophic floods. Unfortunately, as they were trying to recover from that, they were hit by a Category 5 hurricane, Maria, in 2017. So they were just starting to get themselves back together, starting to reconnect the road system and so on. But unfortunately, got hammered by Maria. And they estimate from the post-disaster needs assessment that they put together after these disasters that something like 200 plus percent of GDP was lost during that event. So you can imagine if you're a country and you basically set back 2 years in terms of your income and your investment. So a huge impact on the island. And so these are just some pictures after the event. Notice the woody debris that's kind of littering the streets here, and I'll explain where that comes from in a bit. But lots of damage to buildings, all infrastructure's hammered, you know, networks of power lines and things like that. Road bridges, particularly if they're still standing. And notice there's a water pipe across here, so a lot of the bridges are critical infrastructure. They carry telecoms and water pipes and so on. And so, yeah, another picture of another bridge. This one survived, so that was surviving. But, you know, notice the oops, let me go back one. So notice the large boulders here that were brought down, and then a lot of the woody debris. So these are the trees blown down during the hurricane. Get swept into the river and then clog up the bridges as well. So this is the capital Rousseau. This is one of the bridges looking up to one of the other bridges. I'll just show a video. Hopefully this will come up on the other screen. Hopefully everybody can see that. So this is about 2 weeks after the hurricane. We're looking at the main river in Rousseau, which is the capital, and you can see the debris sort of blocked up against the river. We'll come back to that log there. But the sediment as well is built up, so the channel was a lot deeper than this previously. So the clearance now underneath the bridges is very small. And you can see woody debris that's kind of jammed up against the bridge. It's piled up against the piers. This log's a particularly important one that we'll come back to later, but all this woody debris has been swept into town. So that's arrived on the flood water that filled the town. Okay, so you can see the kind of challenge, I guess, for bridges. But if we kind of take a step back and look at the island generally, you can see this is the road network here in the island. So you can see that because it's quite steep, there's about 3 volcanoes here, so very steep, about 1,400 meters high in the middle of the island. And what you end up with is a road system and a sort of community concentration along the coast here. So you get lots of kind of people living on the flat areas on the coast, which are also alluvial fans if you're into geomorphology. Essentially a lot of sediment deposits over the years, and they are prone to avulsion as well. So the river channel changes quite quickly and quite frequently during these sorts of events. And of course, because they've got this kind of circular network, there's only 1 or 2 roads that go across the island, and they take a long time to get over because they're quite steep. Any break in that road network disrupts access, and that was a huge problem during the recovery phase. Getting to communities where they needed support was a real problem. So how did I get involved in this? So this came about as part of a World Bank project. They were looking as a post-Hurricane Maria to make a loan to the island to help them rebuild their infrastructure. But they were acutely aware that they'd already experienced something 2 years before, very similar. And so the question was, well, are we just going to keep building bridges and having them washed away? Or is there something we can do about it? Is there something we can learn from the experiences of this context? And so I got involved initially as a kind of hydraulic reviewer of the consultants' work that was going on. I then convinced them that it would be useful to have a resilience research project alongside, where we would try and kind of gather, if you like, our understanding of what actually happened and what could be done about it in the future. How could we improve resilience of particularly bridges? They were also quite interested in using drones to fill data gaps. It's a very, there's not a lot of data available on the island. Certainly at the time there was no river gauges, there was 1 or 2 rainfall gauges, but they had intermittent records, so there was a real problem with data. And so that was kind of a context, if you like, for this problem. So we set about kind of studying this as a learning exercise, and in negotiation with the World Bank, these were the sort of assessment principles we came up with. So they were very keen on using whatever the consultants were using. They didn't want us to use any fancy research models. They said, oh, you know, you've got to follow the practice that the engineers are doing that build these bridges, and then we can kind of learn from that process. So we ended up applying, at the time they were using HECRAS 1D hydrodynamic modelling, which works quite well for these bridges. They're quite simple river systems, so 1D cross-sections works quite well. They wanted us to look at flow uncertainty. So at the time, you would have a design event, which might be a 1 in 100-year flood peak that you would then design your bridge to. ASH2 guidance from the US had brought in something called a check event, which is like a much bigger event than your design event. You were supposed to check your design under, and we were interested in doing something more than that, which is to model it under a whole range of flows. So I'll come back to that. And then in terms of calculating loading and scour for the bridges, we followed at the time, it was the Design Manual of Roads and Bridges, BA 5994. That's now been replaced last year or the year before, but I'll come back to that. And we also looked at US ASH2 guidance as well. They were particularly interested as well in identifying upstream landslide risks. They'd had a hydrologist do a kind of modelling study and then a field study where they'd gone and measured rack marks and actually worked out that the flows in the rivers, in some of the rivers, were 3 or 4 times what the model was predicting for that rainfall. And it wasn't a model calibration problem, it was that there was a process happening that wasn't in the model, which is these landslide dams building up, water behind them, then they would burst, and then they would get this huge flow downstream, which wasn't predicted by the model. So quite a complex kind of situation. We came up with this methodology. This is the final one that went into the paper, so it kind of captures all the elements of it. I'll show you a more kind of intuitive version in a minute. But here, what we see is we've got a river and bridge hydrodynamic model, which forms the core study tool, if you like. But around that, we've got data. So we were extracting data from asset databases, from videos, photos, and things like that. We had the drone survey and so on, and then out of that modelling we've got all our parameters, and then that went into the capacity assessments and so on, and the event assessments. So here's just another kind of way of looking at that, I guess. So we had to be quite innovative in trying to get information from wherever we could get it. So it was quite a lot. It was quite manual in collecting a lot of the data, certainly from social media and things. But as you saw from that video that we've got, there's a lot of information out there if you look. So the starting point for the river modelling was to build a digital surface model, and we were working with the University of Michigan, who had a drone expert, and at the time that was quite a kind of a new thing, was to create your digital surface model, and he was doing capacity building with the local government office as well, so that they could do this in the future. So they would fly a drone above the reach of interest. So here we've got oops, go backwards a bit. Here we've got a bridge. This is the coastal edge here, and this is the road that goes around the island with one of the bridges on it. And they were flying drones. This was before Hurricane Maria, which was quite interesting. The timing of it was like a month before the hurricane arrived. So we'd actually got it before, and then they also did some studies afterwards, but we weren't looking at that specifically. That was more of a geomorphology assessment. But they produced these ortho photos, very high resolution, that we could use. And then they processed those to create a digital surface model, and you can see that we've got the bridges in that model. This was slightly new to me at the time. I was quite used to commissioning a river survey, and people would go out and they would do a cross section here and so on, and we would have a very good sort of definition of the channel. So this, although it was much higher resolution and more 2D, brought all sorts of issues to do with trees kind of blocking the river channel view. So we had to kind of do quite a lot of manual editing of these. So although it was a great new data set, it caused a lot of headaches in terms of manually editing everything, so it wasn't quite as automatic as we'd hoped. But we were able to use that to create a 1D river model. You can see the bridge here in the model, so it's a simple cross-section thing. We would put a flow in at the top end. It would calculate kind of what the water level was, and we will also have the structure explicitly in the model, which I'll show you here. So you would have a bridge geometry was in the model there, and we took the peak flow from the hydrology model study that had been done by University of Ohio, I think it was, did this peak assessment, what they thought happened during Maria, and then we would essentially create a synthetic hydrograph that ramped up from 0 to that peak and then receded. So it's not a real hydrograph by any stretch of the imagination. It's a simple triangular approach. What we were interested in is essentially assessing the performance of the bridge over this whole range of flows. So we weren't just interested in this peak, but what happened and how did the hydraulics change. And we'll come back to that. And so you end up with outputs from the model like this longitudinal cross-section along the reach, and you can see it's actually quite steep. This is dropping 25 metres over half a kilometre, so quite steep river systems. And where the bridge is at peak flow, you can see it overtops the bridge. This is a kind of medium flow here. And so this is a kind of classic river modelling approach, if you like. So some of the challenges we had, already mentioned, lack of data, often a serious challenge. The quantity of debris and sediment was massive. You've seen the photos and the video. Scour and deposition changes the channel, and the modelling tools we're using do not allow for the channel to change, or they traditionally haven't. They have evolved since then. And we get these very steep channels, and I'll show you a video of one of the rivers during Erica. Let's see if I can find that. So this is one of these little rivers. This one's actually got a little bit of concrete wall along the sides of it, but you can see it's not really functioning very well, but you see the amount of energy in the flow there. So I think I always find these videos quite informative, because when you're modelling, you tend to think quite kind of simply, I guess, that you're modelling a mathematical water surface. But you can see here it's going up and down, it's causing all sorts of issues. It's not a nice, simple water surface. So it's always worth reminding yourself of the reality of what you're modelling. Okay, so I mentioned we were interested in how the bridge performed hydraulically over a range of flows. So we were, rather than just modelling a peak flow, we were interested in that performance and I'll explain why in a minute. But so here's a plot, which is one of the outputs, if you like, of the river model. Along the x-axis, we've got the river flow in cubic metres per second. So going up to 300 cubic metres per second. This is only a small river, by the way. It's only about 4 metres wide or something. And then you've got the kind of elevation of the water surface here on the y-axis. And you can see I've plotted on there the deck level and the soffit level of the bridge, the top and the bottom of the bridge deck. And you can see the invert of the channel here as well. And you can see two blue lines. The top one is the headwater, so that's the bridge water level, or the water level upstream of the bridge deck. And then the dotted line is the water level downstream of the bridge deck. And so by kind of modelling it under the whole range of flows, we're able to kind of work out exactly what goes on during the event. You can see as flow increases up towards 50 cubic metres per second, water levels going up kind of fairly linearly, and then it hits the soffit, and essentially water becomes constricted through the bridge, and you get this backing up of water. The afflux builds up until eventually the water goes over the top of the deck at about 82 cubic metres per second. So you can see kind of what's going on there. So there's a kind of active area of flow where things change rapidly, and then you can see the downstream water level also eventually reaches the underside of the soffit. So because it's quite steep river system, that doesn't happen until quite high flow, and by that time you've got a huge quantity of water going over or around the bridge system. The reason this was quite important is that the procedures for assessing, for example, a scour, ask you to pick the peak velocity that the bridge experiences at peak flow, but actually the reality is, from what we found, is that you could get higher velocities before this condition, So often the highest velocities were here just before it hit the soffit level, because once it hit the soffit, water was backing up and essentially the velocity drops. And actually that was at the point where these bridges were starting to fill with sediment as well. And we've not even looked at accumulation of debris, which adds a whole nother complication to this sort of thing. But anyway, so when we look at the kind of the bridge results for all of the bridges we looked at 19 bridges on 9 different river catchments. And this is what we find. And so this is capacity versus peak flow. So this is the capacity as defined by the point at which it reaches the soffit. What we find is that the mean is about 21% of what the expected peak flow was during Hurricane Maria. So Hurricane Maria was obviously a significantly large event in terms of flows. What we found particularly interesting is that one of the bridges, which is this one here, so Bridge 2 and Bridge 3, these are the 2 newest bridges on the island and biggest bridges. And they'd been designed by international consultants. They knew about the hurricane history of the island and they had designed these bridges. But even those bridges, one of which had only been completed the year before, only had approximately 50% of the capacity required to carry that flow through. And we'll come back to that a little bit. But here's another way of looking at it. This is capacity versus open area under the bridge. This perhaps not surprising. The bigger the bridge, the more open area there is, and the bigger the capacity of that bridge. And you can see a lot of the bridges are quite small, really. These are not massive bridges. These have about 3 piers and probably 50 metres. And these are more like 10 to 20 metres span. So most of the bridges on the island are quite small. Only a few are kind of really kind of big bridge systems that we're kind of used to, I guess. You seem to have... okay. So with the other thing we were looking at was forces on the bridge. So we were interested in were there specific elements or features of bridges that cause problems. And so we measured what the forces were on the bridges. We used the model to do this, as in to give us the parameters for the calculations. So we're interested in 4 particular forces here. We've got hydrostatic force, which is just the pressure force against the bridge structure. We've got hydrodynamic, which includes the velocity, the momentum element of the flow. And then we also have a hydrodynamic force on debris. So this is assuming some debris is collected on the bridge, and that adds an additional force. And then the final force is a debris impact force. So on top of that is if you've got a large log that's been floated down the river at high velocity and it hits the bridge structure, that imparts a debris impact force. So if we add all those up together, we can see the kind of forces the bridge decks are subjected to. You can see again we've got quite small bridges down here where the hydrodynamic and hydrostatic forces are quite small. And then all the main bridges on the island. Melville Hall is near the airport, so that's quite a big bridge. And then you've got the 4 bridges in the centre of the capital. And you can see, although they're the same span, one particular bridge kind of stands out, and this is the most upstream bridge. I will talk about that in a little bit. But essentially what we found was that had a solid concrete parapet of about 1.5 meters high. It was the only bridge that had this solid concrete parapet. And that essentially gave us this high hydrodynamic, the hydrostatic force against the bridge. So that was interesting. And it was also the oldest bridge, and it had been around a while. So it's obviously kind of reasonably resilient, but not perhaps the best design from that point of view. Just another way of looking at the same results, I guess. Here you've got a bridge span here, so up to 60 metres here, and then most of the bridge is quite small here. So that obviously forces, the bigger the bridge, the more forces. So as well as the modelling, the other thing we did was try and get hold of lots of social media posts. There was one particular person on the island who had a new drone and he wanted to record everything. And so his outputs were hugely important for this study because he flew a drone across the island. He went to each place and he also interviewed residents on his videos. His channel's called Aerial Dominica if you want to go and have a look at it. But that was hugely important to our study. So we used his videos essentially to kind of do an assessment of what happened to these bridges. And this is the bridge that I was talking about. This is the newest bridge on the island. It's only been open for about a year. It had this huge log kind of jammed up against the abutment here. Water went over the top and scoured this huge hole in the abutment. You also see all the debris kind of loading on the pier and the bypass flow. So interestingly, the standards that we're using from the UK, when you're calculating the impact force of logs on the bridge, so imagine one of these logs floating down and hitting the bridge, you make an assumption that, or the calculation makes an assumption that it's a 3-ton log. And when we started looking at these, we were like, well, it's obviously a little bit bigger than 3 tons in this context. So we thought we'd try and tune it. So we did an assessment of these log sizes and found that the average size was about 20 tons from the survey that we did. It was just a survey of the area, so we had to make some assumptions about density of tropical hardwoods and things like that. But it was obviously way higher than 3 tons. When I tried to find out where that 3 tons had come from in the assessments, if you dig into it, you find out that it was on a single river with a single log in Scotland somewhere in the history of time. So that had kind of become embedded in code. It was very strange. But anyway, we used a different kind of calculation based on local conditions. And you can see, you can see the bypass flow that filled the town with all the debris. Here's another bridge, Dublanc, and you can see that the bridge underside is completely filled with sediment and all the water's going around and over the approach road now. So there's actually zero capacity in the end. So our model was rubbish if you think about it in that context, because it hadn't taken into account filling with sediment. So that was one of the issues. And then the final kind of example is Colibistre. Very similar again in that, let's go back, in that you've got debris blocking the bridge here and you get bypass flow on both sides. Going back to what I said about these alluvial fans on the coast, they're the flatter areas, so people naturally build on them. But historically, the river system has moved across that fan, and every time there's a big event, it'll often find a new path. And that's basically all it does, even when the bridge is kind of there. You end up with these new flow paths, unfortunately, through the people's houses. A lot of people died during this event. And these flows arrive very quickly, and there's not a lot of warning as to when the flow is going to... So not an ideal situation to be living in amongst that very dynamic environment. So we came up with 26 recommendations for the World Bank and the local government of Dominica, so that when they commissioned consultants, they would then go through these kind of recommendations. Essentially, the idea was to give them the right questions to be asking consultants to make sure that they're aware of the context, that they understand, things like log sizes are different and so on. And so we ended up publishing a paper on that. You can go and have a look at that for the details. I don't really have time to go into all 26, but I've already mentioned some of those, I guess. But at the core of the recommendations, we found that there were kind of a whole range of underlying issues that needed to be addressed so that we could kind of move this resilience problem on in the future. And it wasn't really a technical problem. We going back to my first question is, do we know how to design bridges? The answer is yes. The reality is that in this sort of context, it's very complicated to design and build a bridge that will be resilient, because if you want to build an ideal bridge in this situation, you've got unlimited money, you just build it high enough and out of the way and it's not a problem. But you can't build every single bridge on the island like that, because it would use the whole GDP of the island. So there's this balance between risk and resilience. But we found it's quite interesting that there were lots of little details about how things were designed on the island that could be improved. Things like each international consultant would have a different set of standards and they would apply it. So you had things like road widths would change from metric to imperial depending on which standard that particular consultant had used. And they didn't have any of their own local standards, partly because technical capacity is quite small on the island. So developing your own standards when you've only got a small population is unlikely. So yeah, final conclusions, I guess, if I summarise this 26 kind of things, was that you can't really build a bridge big enough for the flows that were experienced on the island. Even where they'd thrown several million at this new bridge, it still wasn't big enough. Even though they were kind of very confident that it was well designed, and it was a nice bridge. I would, as an engineer, I look at it and go, yeah, that's a good bridge. That's the one, by the way, with the big log across the corner. And their whole abutment dropped by about a metre, so they had to rebuild that. Bypass flows, I mentioned them quite a few times, this avulsion idea. They're always evident, so they always cause a problem, and they will happen. No matter how good your design of your bridge, you expect bypass flow was our kind of conclusion from that. And that actually when they're designing the bridge, they should be thinking about the community that's living in the area, and they should be involved in that process, because at some point that bridge will be overtopped to a bypass and it's going to go through the residential area. So the design process kind of ignored that, I guess. And we were saying, no, you should be thinking about including that and assuming it's going to happen. The specific conditions are perhaps slightly unusual compared to the UK, in that they're quite energetic. But there are, certainly in the context I'm in here, there are places in Exeter, the surrounds, Cornwall and Devon, that experience similar conditions, Boscastle and things like that. Very similar kind of conditions, maybe not a hurricane, but very energetic and cause huge problems. And the details of the design were quite important. So one of the things that came out of this was something that's been used elsewhere. It wasn't something we'd come up with. It's this concept of a detachable parapet. So the parapet kind of stops the people or vehicles going into the river system normally. But during a hurricane event, they become a trap for debris. So debris just builds up against this and they cause a problem. As part of the kind of initiative, the idea was to have parapets that could break off. And basically, they could take a certain load and then they will just kind of detach. And then they stop becoming a trap, essentially, for debris. And so that was adopted, so that was becoming a thing there. So you kind of, it's almost an acceptance that you can't control everything, but you can minimise the effect of those things. And then finally, perhaps the most difficult thing to include in the design process is the dynamic nature of the event, the fact there's a lot of sediment that's changing the channel, there's debris which is unpredictable. I know there's been some good research here in Exeter on debris accumulation on piers, which is that's kind of the kind of research that needs to kind of feed into this step. This is particularly challenging. And of course modelling methods are now improved. Now we use 2D, and a lot of them have the ability to model sediment as well. But even in this context, we did look at using sediment models. The challenge was that that there wasn't the data for the bed material to feed into these models. So it's back to the data challenge again. So yeah, I guess coming back, just finishing off, this feeds into new guidance, new methods. We have a lot of conversations with National Highways, Network Rail, people like that. They're very interested in these kind of more extreme environments and what can they learn from it. So certainly the new guidance that replaced the one we are using, CD356, introduces a whole range of flows that you have to test against. So that was quite good. And the kind of, I mentioned there's no local standards, so you get kind of multiple UK standards, I guess, and US standards being applied. So this kind of work is useful, I think, for kind of highlighting that. I mentioned before as well, I made a plot here of some of the hurricanes that have ended up hitting the UK area here. And you can see that's kind of, that is something we have to think about. I'm not saying we're going to hit a full hurricane. But we're working with asset owners in the UK, trying to kind of advance this kind of understanding, I guess. See how we can improve things like flood forecasting for bridges and things. So, what about the future? Well, so Dominica, the President of Dominica, Prime Minister of Dominica, he made a vow that they would become the first climate resilient country in the world. And there's this headline about hurricane-proof. And so they're quite serious about kind of making improvements, I guess, in terms of resilience. It's a challenging situation. I wouldn't say they've kind of solved it in that sense, but they're heading in the right direction. Interestingly, this is what NOAA's saying about the 2024 hurricane season, which is about to start. So going into July, August, September time. Unfortunately, they're predicting twice the number of hurricanes that would normally hit the Caribbean because of the elevated sea temperatures providing energy for hurricanes. So I'm going to be watching very carefully to see what happens during that, and hopefully they'll avoid the worst of it. But anyway, yeah, an ongoing challenge. Just before I finish, just a plug. I'm doing a online training course for NASA RSET using Earth observations for flood risk assessment in refugee camps. So if you're interested in more risk stuff that we do, feel free to sign up for that. We're looking at using global data sets in refugee camps, and we're assessing, the full risk to refugee camps. We're looking at vulnerability, how you measure that in a refugee camp, how you make decisions with flood risk information in camps, which is an even more complex context, I guess, for applying engineering. So feel free to join us in that. Thank you for your attention.
Thank you, Mark. It's very interesting. Any questions? Yes, over there.
This is all extremely interesting, and I can only regret that our other colleagues who worked in similar areas are not around. For the sake of others, we went for lunch together, so we mentioned Prakash, but we also have Diego Panici. He is now a lecturer in geography in this crew center. He did a PhD in Southampton on the topic of accumulation of debris on bridges, and then he was, for a couple of years, he was a postdoc in a follow-up project from our project that we talked about. And one of the proposals that I mentioned earlier that we were not successful to was to look at the pressurization of bridge opening, to try to better understand that process. But anyway, this has been recorded, right?
Yes.
Yeah. I'm not asking because I'm going to throw in a political question. I'm just saying we should share this with those few colleagues, and they would find it interesting. I could think of several questions I could ask Prof. So, how are we doing with time? Are you in a rush?
I'm not in any rush now.
Okay. Then I can also ask the very simple first one. So we had Albert and I had a PhD student recently, Laura Wignall, who, among other things, she looked at, she was creating cross-sections on a river using a DHI, well, for the purpose of using a DHI Mike model, but never mind, the issue of cross-sections is the same. On the slide you shown, it looked like more that the vertical planes were aimed to be parallel to each other rather than perpendicular to the river flow, which was kind of curving. Am I right in that? If you pull that one of the earlier slides. So what I think one would expect is that vertical planes that are intersecting with the digital terrain model are perpendicular to, that one. I would think that they should be perpendicular to the river, dominant flow direction, rather than kind of parallel to each other. And if I see correctly, that's not really the case,
Yeah, so having come from a consultancy background, we wanted to do the kind of dogleg sections on the, so you keep the flow parallel. The reality was, part of this was we were training local engineers to build these models, so they weren't kind of pure models. But when we played around with one, not this particular model, we did play around with one of the other models, trying different arrangements of cross-sections, and we found it really didn't make any difference to the final bridge structure area. So you can see we've made an attempt here to kind of, I think the bright green ones are interpolated sections, so they're not so good, but most of the sections that we put in are parallel, or we've got some dogleg in there. So generally the flow runs parallel to the main channel, but once this fills up, it's just essentially flowing in that direction. So it doesn't really make a huge amount of difference, but yeah.
Okay, I'm just curious what thinking was behind it. Not that I know much about it, but it's just...
No, it's a bit like choosing Mannings as well. It's one of those things that you do as good modelling practice, but sometimes you find, I'm talking about kind of choosing Mannings for each specific bit of the cross-section. Sometimes you go into a lot of detail, and then if you just use a mean Mannings, you find it doesn't make a huge amount of difference. You have a channel and then a floodplain Mannings, perhaps. What we've done since then is we've had a lot of students who use this as a test case to develop 2D models. So since this, one of the things we identified was there wasn't very good topography data, and even this DSM wasn't particularly good. We had to do a lot of manual editing. So we recommended that they fly LiDAR for the island. So they did. They've got LiDAR for the whole island now. And so we've been able to kind of reproduce this now in 2D with LiDAR data, which has been really interesting to see how well they match. And actually, you still get very similar results. So even with better data, I think it's a relatively simple hydraulic situation in terms of capacity. You've got a constrained river channel, I guess, that's got a huge flow in it. So it's not complicated in that sense. Building a model, but yeah.
Okay, and then if you just move to the slide with the longitudinal profile, which is the next one, I think, yeah, that one. So I believe I know what HEC-RAS is doing in terms of simulating flow along channels, but I don't know the details how HEC-RAS is calculating when you have sudden changes in the cross-section. Which is relatively, I would think, simple if it's all subcritical. But if it's all very steep and possibly supercritical, what actually does, sorry, I'm trying to ask a complicated question. How exactly does HEC-RAS simulate transitions from, including supercritical flow, pressurous flow, overflow, at the bridge location. How accurate? How they say? What data is provided for that?
Yeah. So if we look at the bridge structure here, because we're looking at a whole range of flows, what we find is that HECRAS will use different routines depending on what the hydraulic condition is at the bridge at a given moment. Okay? It's essentially modelled as an energy loss, and how it calculates that energy loss depends on whether the water has reached the soffit, whether it's over the deck, and so on. It will use a different set of routines. So if it's open channel flow up until the soffit, and then it becomes pressure flow through that orifice, and then when it goes over the deck, you get pressure flow and weir flow over the top. So it essentially starts to add complications to it. So it's still quite I guess, a simplistic way of representing a bridge structure. And in fact, we had real challenge initially with, and that's one of the reasons why we kept the model relatively simple, was actually modelling, having a hydrodynamic model that would run through and keep swapping routines depending on where the water level was, could create instability. So we had some real issues to do with instabilities at first, but we ended up working out how to do it in terms of time step and whatever. So that the problem we had was as soon as the water level reached the soffit, it would switch to the different calculation routine, which would then drop the water level slightly below the soffit, and then it would switch back to so when it switched between different energy loss calculation, it would just kind of oscillate. So we had a bit of challenge with that. So yeah, I don't know whether that answers your question, but it's kind of...
To shed some light on, well,
yeah.
Part of your question, which is, part of what you said is directly answering my question, which is that it does have different...
Yeah.
It's not, how they say, it's not simplified, which is... I'm just curious if it did have several different sets of equations to solve for different...
You even have choices amongst those representations as well, so you can choose different kind of energy loss approaches. Some will be based on lab experiments done in the 70s and so on. So it's really interesting if you kind of start digging into the story behind the choices that engineers are making. And often, interestingly, a lot of them don't realise there's that much choice in they just use the defaults, which aren't necessarily the best in terms of representing flow over a bridge, for example. But in this case, I think most bridges in the UK would not design to overtop like that. You would avoid that at all costs, but every bridge overtopped in this case, so we had to try and represent that. The other challenge we had was there was no data to kind of corroborate exact water levels or exactly what happened. And also we know that the channel filled up with sediment, so that changed the hydraulics, and we hadn't captured that. So actually the situation in reality was worse than we'd modelled, which is one of the kind of interesting... So that's part of what I research now, is kind of how do you capture that dynamics, but it's
okay. Thank you for that. And then while we are looking at this, if we look at the two sections immediately after the bridge, so one obviously has a lot of cross sections to capture details, and then the other one is with a similar longer. So how would you explain the shape of water surface after the bridge, which is water depth is reducing, and then after that it is going up again? So just thinking of basic hydraulic, standard profiles, I don't recognize any of those. So how would you explain those shapes? Yeah, exactly what you're pointing out.
Bit here.
Yeah, that one and then the next one.
So at this point, so the bridge, this is the sea level here. So this is quite close to the sea, and it's starting to spread out significantly. The channel widens quite significantly at this point. If I can find a...
Yeah, it's like a small delta.
Yeah, you can see it starts to kind of widen out at this point here. And then, of course, reaches sea level as well. So there's a kind of complication there. Yeah, this one we didn't initially didn't run it with this many cross sections interpolated. We were curious about, like you, what was Heckrest trying to do with the bridge structure. So we threw in a lot of extra interpolated sections just to see if we could get more shape to that water surface. And it kind of made sense, I guess. That was the bridge deck structure. We had to make sure that it represented the bypass flow as well, so we had to extend that structure out so that the weiring over the top was realistic. It's a lot easier now with 2D. You don't have to kind of play around with that. But yeah. Yes.
I have a question about the flood resilience in the city you've been studying. I'm wondering in which aspect is the most challenging in terms of the flood resilience during the flood? Is it like maybe sliding or structural failure or even other aspects? What is it?
That's a good question. Which I think each bridge had its own issues. The most common one, I would say, is a mixture of where structures had failed. It was often to do with scour early on in the actual flood, and then deposition would often fill up, and some of the bridges disappeared under deposition. You couldn't actually see the bridge anymore. And that caused this avulsion, so the water has to go somewhere and it would carve out a new route to the sea. So that would often end up damaging approach roads and communities and houses and everything, so that it was particularly destructive. So I think from a community point of view, the bypass flow was the most damaging. From a road network point of view, the scour and deposition of the bridge was essentially disrupted that network, which was the main problem, I think, for access. So it kind of depended on the where, I guess. But.
And does the flood resilience have any effect? Obviously, you've said there's the bypass flows, and I was curious if maybe increasing the flood resilience of a bridge will have any or flood damage effect to the surroundings.
Yes, so that is a really good question, actually. I think that's quite incisive because one of the things that we looked at, as you're suggesting there, is that if you make the bridge more resilient and essentially more flow then goes bypass through a community order, you can end up causing more problems, which is kind of why we suggested that essentially you need to model the whole river system and bridge structure and community as a kind of holistic system and look at where that flow is going to go and maybe allow for that. So one of the communities, we looked at lowering one of the parallel roads to the river in the community and essentially using that as a flood bypass, I guess. And even then, that's not been implemented, by the way. That was just something we were experimenting with, essentially kind of making the bypass flow location more resilient as well as the bridge. So, yeah, it's a challenge, I think, in terms of a designer, because often the bridge designer is not interested in a community necessarily. It's not part of their remit when they look at their TOR, their terms of reference for their consultancy role. They design a resilient bridge, but what does that mean? So that's kind of what we were trying to do, is get people to think outside of that traditional design process that's quite kind of formulaic, I guess.
And perhaps, while understanding these flows, is it better to implement a physical model and maybe build a small-scale city with the river and see how the flood reacts instead of maybe a digital model?
Yeah, I don't do much in terms of physical modelling. It's not something I've ever done much of, so I'm not really the best person to ask whether that would work well or not.